Life, a force that can be experienced all around you. In the sky, underground, and on the Earth's surface, we find life everywhere, in all manner of forms. Since the very origin of the universe, even the smallest of its particles has danced to the rhythms of this life force. Regulated by that unique phenomenon that you and I know as motion. The laws of motion have driven the dance of life since the dawn of creation, but it was only some 300 years ago that man began to understand these driving forces, with the arrival on the scientific scene of a unique mind of unparalleled genius, Sir Isaac Newton. Newton made a simple but profound observation. Every object remains either still or in a state of uniform motion until it is acted upon by an external force in one form or another. This external force increases or decreases the object's velocity to a specific extent that can be determined precisely. But the question that arises is, how exactly do we, as observers, determine and measure motion and its effects on the objects around us? Consider the case of two trains moving in the same direction at, say, 50 kilometers an hour. For the passengers in each train, the other train appears to be standing still. For people on the platform, however, both are moving at 50 kmph. So the question is, how should we measure the motion? On the basis of the passengers' observations or those of the people on the platform? The answer was that each is right in his own way. The measurement of an object's motion depends on the observer's state, that is, whether he or she is standing still or moving while taking the measurements. In a nutshell, the answer was that motion is not absolute but relative. But if one accepted motion as relative, another question arose. Were all the other laws of physics relative in the way that motion was? For example, if a person traveling at 40 kilometers per hour were to conduct some experiment based on the laws of physics, while another person who was stationary did likewise, would the results be different? The answer was no. As it took shape in the 17th century, the science of physics laid down the first principle of relativity, that whether observed in a stationary situation or while in uniform motion, the laws of physics remain the same. Born in the age of Galileo and Newton, the classical theory of relativity, as this concept came to be known, remained unchallenged until the end of the 19th century, until experiments based on the work of James Maxwell revealed that in a world of relatives there is one constant, the speed of light, which is identical for all observers, whether standing still or moving at any speed whatsoever. While studying the motion of charged particles, he found that the electromagnetic field created by the movement emerged from the particle in the form of waves. Maxwell called them electromagnetic waves, and when their speed was measured, it was found to be precisely the speed of light. One problem that arose immediately was that of the medium. At the time, it was believed that like sound and other waves, light too traveled in a medium. This hypothetical medium was referred to as the ether. But believing in the idea of an ether meant that the speed of light traveling in the same direction as the ether, which was itself revolving with the Earth's speed, would be different from that of light traveling in the opposite direction. But this wasn't true. Michelson and Morley had proved by their experiments that the speed of light traveling in opposite directions was identical. This meant that there was no such thing as the ether, that the speed of light was not relative to any medium but absolute and was the same in all directions. The turn of the 20th century was a time of great scientific excitement and tumult. The observation that the speed of light was constant created ripples in the mind of one scientist in particular, and the ideas that emerged shook the majestic edifice of Newton's laws of motion by its very foundations. His name, Albert Einstein.